Okay, this week we get in the lab. It's going to be computer-controlled cutting, and we have a very interesting, very complementary group of two new faculty for this class. So Danielle and Debu, and so each will introduce themselves. Go ahead.
That's me. I think first slide.
All right. Hello, everyone, and welcome to the class about computer controller cutting. So during this lecture, we will first have a look to how you can make your design for laser cutting using parametric design and some basic fundamentals about it. Then we will talk about computer-aided manufacturing, so how you can prepare your job for the machine. Then finally, we'll start with the first machine about computer controller cutting, which is the vinyl cutter. And last but not least, we will talk about laser cutting. So at the beginning, we have a personal introduction. And Debu, the floor is yours.
Okay, so yeah, I'm right now on leave, sabbatical leave from my position at IIT Kanpur, and I'm at Neil's lab in MIT. So I am an ultrafast laser person who has been always working towards making lasers, building them, and using them for light matter interactions, laser machining, nonlinear optics, and beyond primary academic research, I also enjoy hands-on practicalities. I have designed custom experimental setups for high precision engineering, which is the way how Fab Academy works out. Next slide, please. Okay, so here are some instruments which we have in the lab, which some of them we have built, including the lasers. So some tie-sapphire lasers we put together to be able to see how they would perform at given times, and we have amplified their outputs and worked with them. Anytime you get some chance to look into our lab, I have the website listed right here, and you can go ahead and look at it. I also enjoy teaching, so I have some online lecture series, as they're called under NPTEL and others, which you can explore. Over to Daniele.
All right, so myself, I did Fab Academy in 2015. I'm an Italian living in Germany. And well, since I did Fab Academy, I started building a lot of machines. And after finding a job being an instructor in Fab Lab Camp Lean for 7 years in a row, I founded my own company that is focused on open source hardware machines. And just recently, we finished our research project about replicating the entire Fab Lab inventory of open source machines. So I'm one of you, I'm proud to say, because I did Fab Academy in 2015, and this was my final project, which is a completely Fab Lab made drone. And also on the bottom, you can see the Sasha kit, which is like the grandfather of the Adrianino, I think, of the current PCBs that you were using. Here, the clue is that once I shared my own designs, a lot of people copied, for example, electronics. And this gives me a lot of nice feelings about open source and how others can use this design all over the world.
Before you go back one slide, just to do justice. This was one of the best final projects. He made a drone, including the control system, and what he's showing is it's not even attached. He's just balancing a cup of water on the drone without spilling it. Very impressive. And so you're in great hands today. Danielle has started a company to make lasers accessible in vinyl cutters, and Debu knows as much as anybody on earth about foundations of lasers, is the team for today.
Okay. So one of my biggest achievements is that the first machine I built, which is called Laser Duo, this large format CNC machine, is currently in the Technology Museum of Berlin. And so if you go there, you can see this as one of the first examples of building an open source laser cutter. So starting from 2015, we have been building a lot of machinery for different projects. And here you can see some of them. I think what's important is, for example, that in 2020, we made a laser cutter that was in the Fab Lab inventory. Then we deployed an entire Fab Lab in Ghana with these self-built machines. And in the last years, we have been building this starter kit, which is this one you can see on the screen. So this is an entire Fab Lab of open source and accessible and replicable and easy to maintain and change, modify open source machines that you can use in the lab. And here we have small, large format machines for every process: CNC milling, laser cutter, including a vinyl cutter, which I think is the only open source vinyl cutter so far that I've seen. So if somebody wants to build it for this assignment, is also nice. So everything is also on the link already published that you can see on the bottom of the slides. And last but not least, we are working on a metal 3D printer, which is still a rough prototype at the moment. And at this moment, we are able to print with stainless steel by using fiber laser source. And so also we will soon go finally on the market after all this year. And our product is going to be this mini format milling machine. So if somebody of you wants to be a beta tester, I will send you a machine at discounted price or for free, and you can start testing. Okay, so, but I'm not alone, because I received the help from Pradnya and Mikael for these slides. And I'm proud to say that Pradnya did Fab Academy at the same year as me. And she's the co-founder of electrical company in India, and she focuses on teaching digital fabrication in the community. And Mikael is the co-founder of a makerspace in Cuenca since 2015, and he did Fab Academy also in 2021, and he is committed to be designing the content for the communities that he serves, that the Fab Lab serves. Okay, so this is the assignment for this week. We just go quickly through it, which means you have to go through the safety requirements to use the machines of your lab, especially the laser cutter, which can be very dangerous. You should characterize the laser cutter features. For example, how much is the kerf, what power can cut which type of material, which thickness, and so on. And this is a group assignment. You should do this all together within the students of your lab. Then you have the individual assignment, which is just cut anything on the vinyl cutter, just anything. Then please design and laser cut with the documentation parametric construction kit. It's important that it must be parametric. That accounts for the kerf, which means the tolerance in order to make the joints tight fit. And then extra credits are about engraving and cutting at the same time, or making laser cutting parts that are not flat, or, for example, make a kit that can be assembled in different ways. So this was an example from one student from Neil, which make this very complex parametric assembly kit. And here you can see more about the documentation, which is linked, and you can see that everything is a separate part. And then these parts are joined together in order to create this structure. I think it's not here, but sometimes it's also possible to make small mechanism in laser cutting, for example, gears and things that move. So take this as one of the best examples for the class. So then we start with parametric design. I saw that you did this before, and you also showed a lot in the class today, but I just want to refresh you the definition of parametric design, which is basically a design that is based on some values. We call these values parameters. So instead of designing something that is fixed, and every time you need to change something, you need to change every single part, you assign a numerical value to each parameter of the design. For example, the dimension, the thickness, or the height, or the width. And then in order to change this design, you don't change it manually, but you change the value. This has an intrinsic interesting point, which is all the changes that are correlated to this parameter will change automatically. So this will mean that you can, for example, scale up a table in length, and then you add new legs automatically to the table. So, and this is a very powerful way of designing. Here you can see in this slide some parameter assigned to some geometrical shapes. Parameters are also important because you might think that they might be only numbers, but no, they can be physical quantities. It can be, for example, weight, or it can be material type, or can be a number of elements. So you can really do a lot of things with the parameters. And as expressed in the previous lecture, this can be done visually or directly in a table, sort of. So here there is an example of FreeCAD, very simple one. So FreeCAD has a spreadsheet inside, similar to Excel or Google Sheet. And in this spreadsheet, you can add basically your parameters. So this is one approach. You can use different ones. This approach includes the fact that you set the parameters before your design. So you think about what are the things you want to change and put them before, but of course you are free to add them later. So here I'm populating, for example, slot width, slot length, and side length over here. Then I assign them a value, which is a measurement unit, which is millimeter here. And then I give them an alias name. This alias name is like the name of a variable you can recall later in order to get this parameter. Then I am designing a simple slot over here in FreeCAD, as you have seen also in the previous class. I'm designing it completely by hand. You see that the shape is not even perpendicular, or the lines are not equal. And then I'm adding all the constraints to the shape in order to make it similar to a joint. So after you add, for example, perpendicularity and equality, then the shape becomes consistent and you can move it, and these parameters are kept constant. Then I am, this is just an example of adding more lines sketched by hand to make a triangle. And then little by little, I am adding all the parameters to the line. So these lines are perpendicular between each other, they are equal between each other, and so on. So it's similar to the previous class example, so I'm going faster, but you can feel free to look at this video. And then after all the constraints are set, you can see that this triangle, it's consistent. You can scale it up and down, and all the things are kept equal or perpendicular. And then after I created all of this, I finally here assign the parameter. So I use the dimension tool, and then instead of typing a dimension by hand, I take the parameters from the parameters spreadsheet that I created before. Here you can see it's auto-populating. And you can see that when you assign the parameter, the design automatically resizes to your parameter. So here, all the slot widths are controlled by just one parameter. So you change that parameter, and you can change, for example, material thickness, and so on. So feel free to explore this video for this example. And then after I assigned, I go back to the spreadsheet, for example, and then change the parameters here. And every time you change the parameter, there is some computation happening in FreeCAD in this case, and this recalculates entirely the old design. So if you close your sketch and you go back to your design, you see here is, for example, 6 millimeter the material width, and 100 millimeter the side length over here. This is, of course, also possible in Fusion and SolidWorks and many other software. So these examples are just a reference for you guys to see a little bit how you could work. So here is the same. We define the parameters beforehand in Fusion. And then similar to the example that was last year in Fab Academy, you create a center rectangle to other rectangles, and you directly assign some values here. And then you can change these values with the parameter. So it's similar. We assign some constraints, we cut the lines. And then basically after all of this that we have our design, we assign the parameters also to this one. So I'm going a bit faster here just to show you, for example, this is the slot depth again, and this adapts automatically. And this is, for example, the other parameter about the material thickness, and then you apply this. Okay, must be clear that you can also use equations and expressions in your parameters. So feel free to use this very complex and powerful tool. So it's important to note this week assignment must be parametric. If you don't do a parametric design for this assignment, you won't pass the assignment. Please start practicing about it. So I have a small section about computer-aided manufacturing, that is the acronym for CAM software, because I think it's important to understand what it is. You will face this also in the Make Something Big assignments, or for example, the molding and casting. So put it very simply, a CAM software is a software that takes a digital design and converts it into machine instructions. So you can design your part, then you go through the software, and through the software, you generate basically the job that the machine will execute afterwards. So you have to know that there are a lot of different computer-aided manufacturing software, depending on the process and also on the machine that you're going to use. In this case, we are going to talk about the laser cutter CAM, of course. So these are the 4 main steps normally that go through the production of a piece. You first design it, and this you learned last week. Then you do through the CAM programming. So the CAM programming implies that you decide which strategy you want to use for producing that part, but also, for example, which settings. So how much should be the power or the speed of the laser to produce that part. And then this programming that you do is translated automatically into the dialect and the language that the machine can understand and execute. And this stage is called post-processing. Normally, this means selecting the machine. And then the last step is this code is executed by the machine. So the post-processing steps and the production step, can be even all integrated, for example, in the same printing driver for a laser cutter machine. But it's important to know that some of these CAM software have these options to select different machines. And here is an example on how it looks like a toolpath for a 2D cutting machine. So a CAM for laser or vinyl cutter takes normally a two-dimensional design. So you would have to export a 2D design even from your 3D files. And then what it does is it takes into account the specific settings, for example, for lasers or for vinyl cutters. So this means, for example, for laser, the laser power, the head, the speed of the moving of the head, the pulses, the frequency of the laser, the position, and so on. And for the vinyl cutter, for example, takes into account what is the force, again, what is the speed of the motion, or what is the cut depth, and so on, basically. So this list is a non-exhaustive list of possible CAM software that you have available. Most of them are supplied to you directly when you buy the machine. So if you buy an Epilogue laser or a Trotec laser, you can directly use, for example, this proprietary software that goes in your computer and can communicate to the machine. But you also have several open source software, some CAM software that you can use with open source lasers or even commercial machines. And then any of these, so every one of these has different features. For example, you can use it in Linux and Mac OS, or some of them are web-based, and basically you can run them in all the operating system, even in your your phone. It could be that you have a Chinese machine, for example, with RDWorks as a CAM, and then you can buy Lightbarn, which is a very common option nowadays. And then what happens is that you have more efficient workflow. So we will see some of them. This is an example of the control panel for the Trotec laser cutter machine. And what emerges from this picture is that you can assign colors to different settings, or that you can have a material library, which means you can define, for example, all the material that it's supplied to the lab, and then input in these settings, and you can retrieve the settings later whenever you want to cut the same material. Similar is for the Epilogue laser controller, laser job manager. Another point here is the resolution. So you can change the resolution of, for example, of the cutting or of the engraving. Of course, the resolution is capped, it's maximized by the mechanical properties of the machine. So you cannot go above that, but you can go below. And this is particularly important for the engraving the pictures. So then also we have Modes, is an open source web-based CAM software developed from the guys from NEO, so the Center for Bits and Atoms. And what emerges from this CAM software also that I want you to note, that is web-based and you can link different items, for example, in this case, SVG, is that some of this software can be used to rasterize or vice versa, to vectorize your image. So you can, for example, see this keychain. This is SVG image. In some of this software, you can do some basic transformation. It's not the same as a CAD software or 2D software, design software, but you can change the size, for example, and or, for example, you can duplicate the object. So if you want to make a grid of this something available in many software. But here, what I want you to note is the colors, are the colors of the image. So you have blue, red, and green. And you see the green is inside and the red is outside. So what I'm doing here is I'm assigning to each color a specific setting. So for example, the green is engraved and the red is cut, but especially I'm changing the order of the cut, which means I'm saying, okay, you should do first the green because it's inside, and then the blue, and then the red. Why? Because if you basically try to cut first the outside, and then the inside, the piece could move, and then you lose the positional accuracy of the inside of the cut. So you can follow this as a template. So you can find a lot of tools online. This is also a non-exhaustive list of tools that you can use to generate simple objects in a quick way. For example, you can find web-based software tools to generate boxes or to generate living hinges, or even to take a 3D model and make a 2D set of slices out of it and then cut it. One tool worth to mention is Dip Nest. It's a tool that basically allows you to put the material as close as possible to save as much material as possible. So nesting is a technique normally used in the industry when you want to produce a lot of parts. And it implies to put the pieces close to each other, but also sometimes one inside each other. And this way you can save a lot of material. So some of you can try this out. This is called Dip Nest and it's open source. So then we go into vinyl cutting. So this GIF here shows you a bit how the process looks like. A vinyl cutter machine is normally a 2-axis machine, which has basically a knife on the head. And this knife is used to cut normally what we call vinyl. You can consider vinyl sort of stickers that you can put basically as a decoration in this case. And the machines are not dangerous, sometimes very small. And here is how a vinyl cutter looks like, more or less. So you have a cutting carriage. On top of it, there is normally a solenoid, so an electromagnetic actuator with a blade that allows the blade to go up and down. And then the head moves right and left in a linear axis. And then you have a roll on the center here, on the bottom, that carries the material back and forth. And through this motion, the machine is able to cut the material. So you can find tons of different cutting plotters or vinyl cutters. Some are desktop and very cheap, and some are open source like ours over here. But some have a much bigger area, for example, like the Zund, and can have advanced options. One option that, for example, some Roland have is to print and cut on the same job. So if you want to cut something and print on it, for example, these are interesting features that you can have. So what you can cut with the vinyl cutter, so the most common materials, of course, are the stickers. You can have heat transfer vinyl that is used for t-shirt, for example. You can cut not so thick cardstock or some chart paper, but you also have special vinyl, for example, with glitter, fluorescent materials, window tint, and you can also cut maybe some leather, some fabric if you're careful. Of course, this is not the tool to cut acrylic or metal or thick plastic, for example. So then the tools have different shapes. Normally, what do you use? A cutting blade, for example, this white one over here. But then you can also change the tool with a writing pen, so you can draw whatever you like. And then you also have tools for transferring, for example, a foil. So for example, a golden foil, and you transfer a pattern. Or you can do scoring for folding the paper later on, or the material later on. Or you can even do the bossing, so to write letters, for example. So feel free to explore different tools for the vinyl cutter. Worth to mention this tool here, the white one, which is an auto blade from Silhouette, is a blade that can automatically change, for example, the cutting force or the cutting depth. So here we have different type of blades, so you can change the blades for cutting. Basically, the more is the angle, the thicker is the material. But you also get some special blades, for example, for cutting fabric to avoid fraying, or for example, some blades to cut thick float. A major difference is between drag knife and tangential knife. Normally, cheaper machines have a drag knife, which means the position of the knife is defined by the dragging of it by the head of the machine. Instead, the tangential knife, the angle is controlled with a motor. And this means basically that you can do very fine details and complex shapes with it. So then you put a cutting mat normally under the material. This is used to avoid that the blade penetrates under the material and cuts under. And it's also used to preserve the blade because the blade will slide on this cutting mat without getting damaged. And then what software you can use? You have many options. Probably you will use what the supplier gave you for the machine. But for example, there is Inkscape. Inkcut is an extension that you could try it out. That you can install for Inkscape, or for example, there is directly Inkscape plot, which you connect to a COM port, and then you can use this directly. This works with HPGL format, which is common format for Chinese vinyl cutters, for example. Here are some example settings for it. Or, for example, you can have more polished software like Silhouette Studio, which is used in the Cameo and Portrait machines. Here you can see the preview of your job, do some simple transformations, and so on. So the settings for the vinyl cutter are speed, force, and depth. And speed defines the motion speed of the head, which means when you want to have higher accuracy or more precision, or you have working with very delicate jobs, you should reduce the speed. Force defines the force that is pushing the blade down to the material, which means you can cut more dense material. And cut depth defines, for example, how much the blade will protrude from the head. So this means how much is the thickness of the material you can cut here. After you cut, you need to remove the extra vinyl from your sheets, which means, for example, the parts you don't want to attach. And then with this, basically, you are able to transfer, after this process, you are able to transfer your vinyl by using some masking tape or some transfer tape to the final application. And this is a satisfying process. You have to do it carefully, of course, and do it in a specific, very low angle in order to don't damage the vinyl. And you normally use these very tiny tools like tweezers to get the angle of the vinyl off. And then applications, we have a lot of them. They are not all here because there are a lot. So the first one is, of course, decorate something. I decorated my laptop during my Fab Academy, or make a t-shirt with a heat transfer vinyl. Worth to mention that the heat transfer vinyl requires a heat transfer machine that maybe most of your labs have. But of course, you can use this as a mask. So you can paint or etch with a mask, or you can, for example, use it for PCB. You will see maybe this much better in the electronics production week. Okay, and I think my part is over, and I hand over to you, Debu.
So first, a couple quick notes. Danielle, great time management. The vinyl cutter is the least appreciated tool in the Fab Lab, and in some ways the most useful. And in some ways, the laser cutter is the most overused tool. So don't neglect the vinyl cutter. Okay, Debu.
Yep. So let's see what's the hype about the laser. So first thing first, what is the part that we're going to look at is something where the idea of a laser, how small can it go by using a lens. So there is something called a Rayleigh region over which the focus of the laser becomes the smallest, and that is the region over which we are mostly using to do our machining and the cutting, and that is defined by something often known as the diffraction limit and resolution limit. These are technical terms, but it's worth it to remember that it essentially is dependent on the wavelength of the light that is being used. So depending on the wavelength of the laser, the resolution would be dependent, and that can also sometimes be the estimated width of the cut. Next slide, please. So the typical laser cutting lasers are like CO2 laser, which you are often aware of. It's a continuous wave laser. Then there are fiber lasers, ND-YAG lasers, which have different wavelength operations in the infrared, visible, as well as in the UV. Then there is this dye-sapphire laser, which has a wide range of wavelengths, but it is in the femtosecond pulse region. And then excimer lasers, which are UV pulse lasers. And there are diode lasers, InGas or aluminum garnet, arsenic lasers. These are either in the visible or in the near IR. Next slide, please. So you already saw the epilogue system as an example of machines. And so they are some of the classic laser cutter builders. One of them is the epilogue laser. And the next slide. And the Trotec. And most of these systems have evolved from the fact that the development of the laser has resulted in faster, better, and lower costs of them. So that's actually a major important component. And the reason why laser cutters have often become very useful is also because it could cut through a lot of different kinds of materials such as wood, metal, stone, glass, leather, paper, textiles, plastics. And so it's a choice of the right kind of laser conditions and the cutting conditions that result in these advantages. Next slide, please. So what is it that is about the laser? Laser itself, you can think about it in the electrical engineering trends, an op-amp, operational amplifier, where you have an gain medium, which is the laser medium, which due to an external energy source can be pumped to an excited state such that its excited state is more than that of the ground state. And then when this happens, it emits light, and that can be put inside a amplification scheme where it keeps on amplifying itself so that light comes out or radiation comes out, which is the part which we call as a laser. So it's light amplification by stimulated emission of radiation, and the gain has to be greater than the loss of this entire system. So the output part of the laser is the one which is most important. Depending on the medium that we use, that's the one of the reasons why we get different kinds of lasers. Next slide, please. So in essence, the gain medium, or the medium which is the excitation part, has minimally has to have three systems, the three states. If you have a simple two-state, then it's hard to make a laser with that. So the first laser that was discovered, the ruby laser, had three state, but it can only operate in pulsed mode because the upper excited state will lose out of energy and it will again have to be replenished when it can again start lasing. But if it's a four-level system, like most of the modern laser systems use, you can either operate it as a continuous wave laser or a pulse laser, depending on how you design the laser. So that's actually one of the advantages of the current lasers, that they are mostly using systems where you could operate in different ways. Next slide, please. Now, we will look into the various aspects of laser machining with cost-effective and versatile systems. And one of the products, one of the companies that I've chosen is the X Tools, because it has a lot of presence in Fab Academy and Fab Labs, especially in Neil's lab, where I'm presently in. And it also provides very reasonably priced solutions for most of the things that you'd like to do it. And it has a very wide range of applications. So we will start with different parts of the X Tools. The simplest one, yeah, next slide. The simplest one is the one where the design is based with the motion controllers. So you have a laser, and then the light is made to do the cutting or designing by using a motion controller design. So this is a sort of like a crude picture of how it would be looking like. Next slide, please. And what other additional features that you really need, as you have also seen for the other part of the talk by Daniele, that you would need to have the aspects which are important for machining, which is that it has to have safety features, which I'll come to the end. But mostly the settings for the laser and its motion are going to going to be important in terms of its focus, the power that we use from the laser, the speed at which you operate the system, the rate at which you bring the laser pulse path coming, the window over which the laser is on or off, the number of passes you go through to make the machine repeat or do it in one pass. Then you have to also make sure that your design condition is set properly so that the coordinate system origin are all set, the vectoring of the design, and the rastering of the part that you have made. And last but not least, the camera, which kind of decides, multiple cameras are always better in deciding on how you are going to go ahead with the execution of the process. And finally, there should be enough coolings for the system through airflow, and there is an exhaust and filtering system in the process. And the different kinds of mechanisms work when the lasers are employed, depending on the medium as well as on the wavelength of light, or whether it is a pulse laser of different kinds or it's a CW laser. So it is either through bulk burning, melting, evaporation, and ablation. These are the different ways how things work. Next slide, please. So here is one of the first example, the CO2 laser, which is often one of the easiest and the oldest systems which have been around in terms of laser cutting. Next slide, please. It's also very affordable. So it can do a lot of things, including curved surface engraving, 3D surfaces, and it has a very high precision in this particular machine that they have, which I have taken. One of the other advantages of this is the size that they are able to do the machining of, the breadboard size of the items that they're doing. And here, as I mentioned, they use a dual camera system to make sure that the visibility and it can be done well. It can cut acrylic of all colors. Wood you have already seen. Next slide, please. So the camera is obviously a major important part in this. So your engravings and other parts that you would like to really use for making the system work is very easily available. Next slide, please.
Debo, for pace, you need to go 1/3 faster.
Yeah. So I'm going to go through these fast now because I've already talked about it a lot. So essentially, these are the different features that are present. For the next slide, please. So one of the important things is that it's a very powerful system, 55-watt output. So it can cut through, and it's a CW laser, it's a continuous laser. And so it can cut through 20 millimeter acrylic or 18 millimeter of wood. Next slide, please. And this is only in one pass. Can also have a big length that it can do. Next slide, please. So these are generally the other parts which are important. That's the exhaust fan, air pressure is available, and the safety features like the optical path indicator and a way to make sure that you do not do things when the laser is on. All these things are also the daily maintenance has the quick release button. These are important features. Next slide, please. Okay, next slide. So just showing how different aspects are possible. Versatility. Next slide, please. And the other reason why this company has an advantage is the software is quite easy to use. Next slide, please. And often the parameter settings are already predefined, although you can play around with them. I'll come to that later. Next slide, please. Okay, so the next kind of tool that I have chosen is the one where the diode is actually used to be moving rather than the traditional way of having a motion system. So this is important because it's a very high power laser system. I'll explain that as we go along. Next slide, please. So here what happens is many diodes are actually put together in one place. So they becomes coupled coming through in one place. And so all the diodes are coupled into one output point, which is then is able to generate like 40 watts of output of the laser. Next slide, please. So, well, these are all the parts which are there. So 40-watt part is the most important. Next slide, please. So what the advantage again here lies is that you could use it to choose the amount of power that you want, depending on the diode laser that you choose, whether it's 2 watts or 40 watts. You can choose the range of items that you can work on and choose the materials that you would like. Next slide. So it also has the one press, the positioning is extremely good because they use multiple camera, and that's why you can actually get a perfectly centered positioning and alignment. Next slide, please. And the other part, which is the finding of the focal point, and it's done with very high accuracy. The reason why the very first slide that I showed earlier about the laser and its focusing is important is that you want to ensure that you can get your focusing done very accurately and properly. And next slide, please. So there are many ways where this one has become very useful. Next slide, please. So 40-watt laser, you can have 15 millimeter of acrylic and 18 mm of wood. Slightly less than the other one, which is 55 watt. Next slide, please. And it also allows a large size to be worked on. Next slide, please. And engraving is very easy even on a flat surface. Next slide, please. Okay, one of the very interesting parts of this is that it allows rotary engraving on this because the diode is all coming from one point. If nothing is moving from the upper or top part, you can introduce motion and design controllers at the surface level, which can then have the rotation parameter also, and that's why you can have these cups and other things can be done in a circular manner, nicely designed in this way. So this is one of the interesting features of this set. Next slide, please. Yeah, so again, software is an advantage here. Next slide. And it uses AI in most cases. So there are many other of these additional accessories here which is on the side where the laser doesn't have to do the motion, but it's on the accessory on the board where the machining is being done, where you can have all the motion. Next slide, please. So it's basically the same thing in the entire. Next slide, please. Okay, the next part, type 1, which I have chosen, is the one where you do the machining by using Galvo stage uh, uh, control. And in this particular one, we also use a different kind of a laser. So I'll go into this, a 60-watt MOPA laser and a 40-watt dual diode laser engraver. Next slide, please. So here the Galvo scanner is useful because both the lasers can come to the same place so it is easy to have both the laser come to the same point, and the controller is going to have this use this in such a way so that you can move from the top. So that's the controllability using the Galvo laser. However, it works best for curve designs because it's a circular control from the top side by using a motion on the Galvo control. Next slide, please. So this Ultra has certain advantages, but I think I'll show you the comparisons with the others, which will be much more better. It has working speed at 1500 millimeters per second. Next slide, please. Okay, the safety part for all of these, as was mentioned, is that they are all enclosed. So even if the laser part is there, it's an enclosed system. So it gives a good, okay, next slide. So since there are two lasers being put together, so it has the advantage that it can do both metal cutting as well as design and engraving all in one place. So I'm going to show in the next slide. Yeah, so the MOPA actually has the advantage that it's a type of a fiber laser that offers highly precise control over its pulse characteristics as duration, as well as the frequency of the laser, which enables a wider range of material processing capabilities compared to the traditional laser. So this advantage makes it very useful for its use and precise engraving into and as well as cutting with deep engravings. Next slide, please. It also uses high-end cameras, which makes the precision very high. It can go down to 0.2 millimeter size precision without any problem. Next slide, please. So in this version also, they have been using AI to support their designs to the maximum level. So they can really use it with how you would want the things to be done. So it's very user-friendly in that sense. Next slide, please. Because of the AI and all these advantages, it also can do replication of the designs with very high accuracy and ease. Next slide, please. It's okay. I mean, the number of outputs can be extremely high. Next slide. And it is also something which is possible to be used in many environments. They claim that it can be done at open space also. But I would say that it's always useful to keep an eye on safety features, which I'll come to in very soon. Next slide, please. A lot of materials can be addressed by this technique because there are two different kinds of lasers and they have a wide range of materials that can be looked at. Next slide, please. Yeah, and since there are various different options, whichever works better is the one for the particular system. Here in the lab, we have various different kinds of DX tools. So depending on the particular use, we use different systems. Next slide, please. Okay, now come to the fiber laser metal cutting part. Now this is very interesting because this basically takes over the entire process of welding and cutting. Next slide. Which allows a large range of results that can be looked at by using the system which has which allows the head to be taken out and done in a different way. Next slide, please. Yeah, so here I give the example that you can actually take out the welding head and you can do the engraving or welding not inside the box, which is also available, which is the way typically we do, but this is by using your own hands to do the same job in a traditional way. Next slide, please. Yeah, so it handles welding, cutting, cleaning, and engraving all in one device. It can go up to 45 millimeters of laser cleaning by using this technique. Next slide, please. So it acts in a beautiful CNC laser engraving and pencil laser cutting principles, and this has very much better resolution as well as the amount, the range of materials it can handle, as you can see it here, are very large. All very large range of metals are available for use with this system. Next slide, please. So I have many examples here. Maybe just for browsing, we can keep going. Next slide, please. Yeah, so it can help in making even jewelry or making sharp features, chandeliers. Next slide, please. You can also do sheet drilling, auto body repair, and rest I have already covered. Next slide, please. And it can also do aluminum and stainless steel, which is anyway done. Next slide, please. Okay, so this has a very high versatility in terms of its application, and for rapid prototyping and engineering applications, it is also of kind of useful. Next slide. In various metals, and well, here I found an interesting comparison where they have shown how the welding of the regular gas tungsten arc welding versus the welding by using the laser welding has been compared. So the feature sizes as well as the burns are almost not seen. In the next slide, you see the range of thickness that it can do the cuts in terms of cleaning as well as thickness. It goes all the way from 0.008 inches to 0.39 inch thickness. Next slide, please. Yeah. So the CNC cutter from Xtools versus the plasma CNC cutter, the difference in the quality is extremely obvious. The burn marks are almost not present, as well as the curves are much more smoother by using the laser cutter. Next slide. And even when you make small tools, here is an example of a 25 mm small tool versus a plasma cut 250 mm tool. The Even though there is a size difference of 10, so the X tool CNC cutter item has a much better, finer cut compared to the ones which are with the plasma CNC cutter. Next slide, please. So we wanted to actually just show you that the parameter space of these are very important, and by adjusting the size as well as the window of the operator of the conditions that we use, you can in fact see how the process of laser cutting is working. So for this particular metal cutting system that we have, this metal fab, we set the size to the smallest possible window of the laser opening, which would allow the number of shots to be also the minimum in terms of the laser pulses. And under that condition, if you were running at a very high speed, say around 300 in terms of the number that they have set up, there was no cut possible. But as you brought down the rate at which the speed of the machine, then you can start doing the cut. So if you move at a very slow speed, then at 1, let's say we set it as 1, then it cuts very nicely, no problem. This is a thin metal, it should cut. But as you make the speed higher, then the cuts start getting into trouble. So beyond 110 or so speed, it doesn't cut at all. So on an average, there is essentially no laser pulse which is hitting the metal because of the window and the size of the repetition rate of the laser. But in between 20 and 50, you'd basically be able to see a few pulses um, hit the metal, and you can then start finding out how your feature size is. So that's what we did in a small little exercise here. Next slide, please. So we took the SEM images of these uh, cuts that we had made, and they were essentially making the circles to make the circle in a very uniform manner with exact spacings being the same, and it was very reproducible in terms of hitting the same spot. And you can see as in next slide, please. I'll show it better in the next slide. Yeah, so they kind of show uniformity in terms of their spacings in doing the hits, and the same spot being hit multiple times if you do it as you change the window of and the pulses. Next slide, please. And you can see the melt features because in this particular form, the metal which is getting melted, this is not a very long pulse. This is not a very short pulse. So when you go to really extremely short pulses, then different mechanisms work. Then melting processes are lesser and lesser. But under this condition, the metal melts, and you can see the melt still remaining there and its features moving out of the hole, and you can kind of estimate how these are. So these cavities that are formed, which are not through holes, before making the through holes, this just one shot at a time, are about 100 to 110 micron size, depending on the wavelength. So we have used this IR radiation, so it cannot go smaller than that. Next slide. So this was just an example of how you can look at how your machine is working. But for the safety part, it's very important to make sure that the fire safety hazard is always taken care of. There's a fire interlock available, there's a fire blanket available for smothering in case any fire hazard breaks apart. And most of these lasers, as I said, are contained well enough to be considered as class 1 lasers. So supervised lasing usage is important. And but you should always be on the alert for any smell or smoke, and should have a good exhaust running to ensure that there is no smoke or smell. Next slide. And some of the other high-end examples and possibilities exist. So I've taken some from Neil's lab itself. Um, there's this whole range of water jet guided laser cutting system where you can have an internal reflection of the water jet laser getting into that the water jet and then contained within it, so that it can cut through any length of metal, and it's a very good way of cutting. Uh, same with the then there are these other two examples that I picked. One of them is the 534 nanometer nanosecond pulse laser micromachining, which is from Oxford, which is a commercial unit, but it has a very good laser system with high precision systems, which can do high-end jobs. And there is a femtosecond laser, which is the Pharos laser, which can be assembled and put together to form a laser machining system. This laser in itself is on its own a femtosecond laser, but it can be used to make a laser machining system. And I think with that, next slide, I would conclude, and thank you very much.
So thank you, Debu. And Danielle, let me take over to add a few things beyond this. So coming up here, share. So just a few notes beyond what Danielle and Debu covered. So in addition to raster engraving, a new-ish thing emerging is diode pump lasers can be doubled or tripled with nonlinear optics. And when the wavelength gets very short, you can do something crazy, which is you can actually focus it inside glass, and you can etch the glass in 3D from the inside, not the outside, and make things that look like that. And so these UV lasers used to be $100,000. They're now coming down to a few $1,000s, and I expect there's going to be a big impact from UV lasers, is one note. Another thing you can do with the laser is you can halftone. You can drill holes of various sizes, and you can use this. If you illuminate them, they look beautiful, and then you can use it to screen print a shirt with continuous halftone images. Now, for this week's assignment, what I want you to do is design a construction kit, and you need to account for the laser cutter kerf. And so the key point is when you make a joint with the laser, and I'll talk about the joints in a second, this dimension needs to be within about 0.001 is the tolerance for that. But the laser beam itself is about 0.010. And so if you want to make something of that size, the laser beam has to be offset by half of its width. And so when the beam cuts, kerf is what you call the width that's removed. And then offsetting is moving the beam so you don't cut on the line, you cut off of the line. And so what you should do for this week is vary the thickness of slots to find the right joint size, accounting for the kerf and offsetting the beam. Then once you do that, I have an example here. This is a 3D construction kit made out of cardboard. Here's a FreeCAD file. And the whole thing is very parametric. So all of these parts are designed relative to the spreadsheet. And so if I get different stock by just a little bit, I can take the stock dimension and propagate it all the way through the beam, the design. And then here I'm showing you can either offset in the CAD tool or you can offset in the CAM tool to account for the dimensions. And so that's a key skill for this week. For the materials, there's been discussion in the chat. Let me stress cardboard. So you can laser cut wood, you can laser cut acrylic, you can melt it to bend it. Acrylic is fairly brittle and it's environmentally unfriendly. You can cut Delrin that's more flexible. It's fairly messy in the laser. It makes you need to clean more. Cardboard, it's easy to underrate cardboard. So I, for example, order these structural pads. When you get cardboard in the US system, it's rated by what's called the edge crush test. And an easy way to explain it is if you have bad cardboard, if you bend it, it kinks right away. If you have good cardboard, when you bend it, it bows rather than kinking. That sort of cardboard is environmentally friendly, recyclable, renewable, but in particular, you can make beautiful furniture. You can make really substantial things out of it. And so I strongly recommend cardboard for both prototyping, but you can do really good structural systems. Most fabrics laser cut well. Pasta is a fun material, cuts well. PVC plastic, you never put in the laser because it releases chlorine. There's ways to test for it, but really the best rule of thumb is don't cut a plastic if you don't know it. Metal, Debo showed the metal cutting laser. That's great. It is a kilowatt laser. Anything less than that you can't cut, and it can be hazardous for your laser if you bounce light in it. Likewise, polycarbonate needs a very powerful laser, otherwise it just chars and smokes. Now, I want to say a little bit more about safety. So laser cutters are always trying to catch on fire. So for the laser cutter, typically there's an air assist where the laser beam's coming in, and then there's airflow from above, and then there's exhaust from below, and it's taking the combustion products and pulling them out. You can get closed filters for the laser that take the air and push it through a filter. They're not great. You can use them standalone, but they're not 100% effective, and the filters have a lifetime. So when you can, it's much better to vent outside, but you don't want to vent anywhere near people. You want to vent away from people, venting up if you can. Now, in this volume, you're creating gases, you're creating combustion products. If everything works well, it goes through the exhaust. If you look in a laser cabinet and you see smoke, it's a terrible sign. It says the exhaust isn't working. You should stop right away. Likewise, if you come into a lab and you can smell the laser cutting, you should yell at whoever is laser cutting, because after you cut, it outgasses, and it takes about a minute for that to be carried away. So if you open the laser right after cutting, you're releasing unhealthy things in the lab. You finish cutting and wait a minute or so, let the exhaust products get carried out. Now, in my lab, there was a student who was laser cutting. It was a big job. He went off to do his email, and then he wondered why there were fire trucks outside. What had happened was the belt on the laser broke, the head stopped moving, all the energy went into one place, and it eventually ignited. In this case, my students did what you really shouldn't do, which was they are heroic and they fought the fire, and that's why the building didn't burn down. And so Adrian showed a picture a short while ago. You should draw a line on your floor next to the laser if you don't have one. And you should have a policy that you can't use the laser unless you're within that line. when the laser is cutting, if it begins to ignite, the lasers are almost universally interlocked. So you can open the laser and that'll shut it off. However, if it's a really bad fire, what'll happen is if you open it, the fire's still burning and you actually feed the fire with more air. So then Debu mentioned a fire blanket. The idea of the fire blanket, it's not for you, it's to smother it. The blanket is a heavy material, the size of the bed, and you can actually use a piece of stock the size of the bed, and you put the stock on top of the fire, and that smothers it. And usually, as long as you're paying attention and you see it start to happen, you can smother the fire, and then that's fine. If you're not paying attention and it begins to ignite the system, then you call the fire department. So every lab with a laser cutter has had fires. Lasers are always trying to catch on fire. And the key thing is they always need to be supervised. Yell at anybody you see laser cutting with their back to the laser cutter. Now, class 1 lasers don't need any protection. They're completely sealed. Class 4 lasers are open and you need eye protection and you need an enclosed workspace. There are a number of vendors that sell both desktop and large format class 4 lasers. I strongly recommend staying away from them. You need to manage them like you manage a laser lab, like Debu's, again, that need eye protection and interlocks on the doors, and you need to control. So you should be using class 1. So then the next note is you're releasing all these combustion products, and on a CO2 leser with a path length, they get deposited on your lenses. So a key skill is learning how to clean the lenses. If your lenses get dirty, it's not dangerous to you in the sense of a fire, it's dangerous to you in the sense of your lab budget and an instructor getting mad, because the dirty lenses absorb more energy and eventually you'll blow up the lenses and you'll need to spend a few $100s to replace the lenses. That's less of an issue with the diode lasers moving. So in this range, CO2 lasers are powerful. They're good for cutting wood and acrylic. And the tube has a lifetime. Over a few years, eventually the power begins to droop. The diode lasers, typically the wavelength is roughly green. Those are getting much more powerful. They're simpler because you don't have to route the beam to the head. You just move it, less trouble to clean it. They can cut a range of materials other than they can't cut acrylic. They can cut dark acrylic, but clear acrylic, it goes right through. Fiber lasers are very powerful. It's a very interesting design. It's an optical fiber that guides the light, and then there's a gain medium actually in the fiber, so the fiber itself amplifies it, and you can get more power the more you go through. The fiber lasers can be very powerful. So Debu showed the kilowatt fiber laser. And so fiber lasers, the tabletop ones can cut thin metal. The more powerful ones can cut thicker metal. And then the UV lasers that are emerging are really good at, and let's see, going back, the fiber lasers, you'll see when we get to PCB fabrication, one of the best ways we make very high resolution PCBs is we use a Galvo scanned fiber laser to do very high resolution removing of the copper. The Galvo lasers, compared to all these other ones, can move much more quickly. So they're good for fast rastering, very high resolution scanning, but they have a smaller work area. And then finally, affordable UV lasers are just emerging. Previously, I had an excimer laser that had fluorine gas. It was a nightmare to run. These UV lasers can cut almost anything because they're such short wavelength and they're very high resolution. And I think they're going to begin to displace other types of lasers as those mature. So these settings don't have a single best value. Usually you want to be in focus for high resolution, but sometimes you defocus to remove some artifacts from cutting. If you cut with too little power, it doesn't work, but too much power can char and burn. Sometimes you need to do multiple passes rather than one pass. If the rate you pulse is too fast, you can put too much energy in the same location. If it's too slow, they're too far apart. And so each of these parameters has a regime where it's happy and either side is unhappy. And so the idea of the group assignments is your lab needs to do it, but not everybody separately. You need to go through the range of settings for your materials to find where it's happy. And then the kerf, oh, sorry, one last quick thing I skipped back here is when you're making joints, a simple slot fits together, but it's hard to align. If you add what's called a chamfer, that helps with the joint alignment and helps to compress the material. If you add a little bump, then it snaps, which makes a better joint, but the snap depends on the material properties. If you add a little beam, the snap, you can adjust the stiffness of it. And then the most strongest joint of all is a pin joint where you put a snap into it. And so I've got linked here a FreeCAD file with a range of types of joints. And so an example, all of that you saw a moment ago was, here's a fun project that's a construction kit. This is a binary counter in cardboard. So what I want you to do as a group is, for the materials you're using, characterize all the settings, including the kerf of the laser and the different types of joints. On the vinyl cutter, cut anything. Make a sticker for your laptop, for example. But then I want you to design a construction kit. I want it to be parametric, so you can adjust to the materials, account for laser cutter kerf. A fun design task is design it so you can assemble it more than one way, not just a box, but a general kit. And then another thing you can do is if you make, these are called living hinges, where you cut a pattern in the cardboard and it lets you bend the cardboard up into 3D. And then you can design flexures around that. And so I have linked here, this was a great, somebody who really overshot on this assignment. Let's see, let me find the video. Okay, down here. She made a wooden dungeon construction kit. This was above and beyond the minimum for this week's assignment. These are all the parts to make the construction kit. And then in a moment, it'll show a couple things I just mentioned. She has mechanism. She has a rack and pinion. Here's a flexure to make curving parts. And there are mechanisms in it. So another kind of extra credit is making elements that aren't flat, play with flexures. And another kind of extra credit is engrave 2D and 3D designs, as well as cutting out the outside. But the main thing we want you to learn is beginner laser cutting is cutting on the line. More advanced laser cutting is accounting for kerf and making beautiful joints. So for time, you're going to laser cut. There's a Saturday open time for any of the issues that came up. And then we have a very important recitation that's a prelude. Next week's class, we're going to start embedded programming, where you write programs for microcontrollers. I can guarantee you're going to make programs and make circuits that don't work. There are all sorts of ways you'll have things not work. And so you need to debug to make something not work. And so a prelude to next week is introducing programming languages and then introducing debugging tools. And all of that's background to then get ready for learning about embedded programming. Okay, any questions, comments at the end?
Can you go
I just
over?
answered a lot of things on the chat and added my comment on the chat. But if you have more questions.
Okay, real quick. Vivan?
Yeah, can you please elaborate on a construction kit? Like I'm sort of lost on what a construction kit specifically is.
Construction kit meaning you're going to be given sheets of flat stock like cardboard, and you're going to make a thing. So it's parts you assemble into a thing.
So it's like something that has to be or should be able to, someone else should be able to do it as well. Like not like should be designed to be universal.
Yeah, don't overthink this, meaning I want you to make parts you can assemble into a thing. And you know, I've linked a couple. I showed you the castle example and the marble. Calling it a kit is it's more than just simply making a box. It's a set of parts that can make something interesting. Tarek?
Okay, yeah.
Hey Neil, can you go over the kerf again, just in terms of the offset?
Sure. So
Yeah.
again, I recommend if you make a comb where you make joints, I'm exaggerating, where each one, like this is 0.010, and then this one is 0.009, this one is 0.008. What you'll find is if the joint is too large, it's sloppy and doesn't hold together. If the joint is too skinny, you can't fit it in. And there's a window of only a few thousandths of an inch where you make a good joint. And again, I quickly showed that FreeCAD, a slot is hard to align. If you make a chamfer like that, the chamfer helps with misalignment, and it also helps to compress the material. So now what the kerf refers to is if this is my laser beam, when it goes through the material, the kerf is the width of what gets removed. And I said 0.010 inches is a typical kerf, but we need the joint to be within about 1/1000th of an inch. So what it means is if you want the edge of your part to be here, the laser beam has to be offset by half of the kerf so that this ends up where you want it to be. And you need to do that to make good joints.
Gotcha.
Okay.
Thanks.
Good.
Neil, sorry, just a quick question about this. This is something we should consider within our drawings or with the software
you can do it both
that we
ways.
use?
So
exactly, yeah.
Yeah, you can account for kerf in the CAD and then send it to the laser cutter and cut on the line. You can account for it in the CAM, and the CAM can offset for the kerf. And also, most of the laser drivers also know how to account for it. So there's 3 different places you can account for the kerf. And part of this week is to actually see all the different ways to do that. They all work. You can do it at multiple stages.
Yeah. Okay. Thank you.
Okay, so Dorian.
Hi. So my question is when the focus of the laser, like, so you're supposed to have the, I'm sorry, there's a double echo in here because we're listening. I'm at the school. So when you have the laser and you're cutting and you are zeroing out the laser, so it's at the top of the material, but as it's cutting down into the material, that means that the point of focus is going to end up moving as well.
Got it. Two notes on that. So the first one is, as Debu showed, there's what's called the beam waist. Typically, you want that at the top of the material. However, in some cases, you intentionally defocus because you can get artifacts if the beam is too skinny. Now, to your question is, if you look at this beam waist versus the material thickness, for many applications, the variation between the top and bottom isn't that large. And so you focus at the top and it's okay. However, when you're doing deep embossing, that's not true. And so if you go back to take the example of the X-tool Galvo lasers, let's see, I like X-tool lasers. I don't like their website. That's messy to navigate. So in these Galvo scanned X-tool lasers, the whole head that contains the Galvo scan can move up and down. So it actually does something to do, let's see, when you do deep embossing, let's see if I can find an image quickly. No, let's see. We're going over time, but I'll take just a minute and then we'll wrap up. When you do deep embossing, let's see, this is taking too long to okay, sorry, this is what I wanted to get to. When you're starting to do this sort of embossing, what it actually does is it has a vision system to match the surface if it's not flat. And then as it does the laser cutting, the whole head is moving up and down to move the focus as it moves through that. So you don't need to do that for thinner cutting and flat stock. You need to account for that for deeper cutting. Okay. So once again, help session over the weekend. Come to the recitation Monday to prepare for the embedded programming. Right off the bat, as a group, characterize your lasers. And then this is a fun design week. Don't overthink to that question, kit. Kit means parts you can assemble into something interesting. This is a fun design week. And one thing you can do is look ahead. So for example, the geodesic dome, when we get to making big things, it's a great idea to make small cardboard laser cut prototypes of big things. And so you can use this example to make small models of big things you want to make later. And don't forget the vinyl cutter. Easy to neglect it. It's one of the most useful tools in the lab. Okay, happy cutting. See you all at the recitation the next week. And thank you, Debu, Danielle, and Michael Pradnia for pulling all this together.
Thank you to everyone.
Bye-bye.
Thank you. Thank you.
Thank you.
Thank you.
Adios.
Adios.
Bye, guys.
Bye-bye.
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 Bye. Bye.
Good night.
Bye.
Bye.
Bye.